pitch bend, you only have to send 3 bytes. Because you don't have to specify the controller, it's a pitch bend controller. And so you just give it the LSB and MSB. Now, some controllers actually only use the MSB, sometimes they don't even program it. So it may sound a little kludgy, because if you take a pitch bend that's plus or minus a whole step, and divide it into 128 gradations, that gives you about a fifth of the semitone per bit. So that's pretty noticeable. Yeah, depending on how fast you're bending. So that's why it's available with either. Okay, now here's an aside. I'll talk a little bit about. Now I kind of glossed over on the previous slide. I said, assume your pitch bend is plus or minus a whole step. And I think that's a fairly common one. Like pitch bend, they normally center, and you can go low, you can go high. But you may want to have your pitch bend be an octave up or down. Or you may only want it to be a quarter semitone, something that, so it's very minor. So how do you do that? How do you program it? We have controllers which you use for real-time expression. Well, they have these parameters that are used for kind of they have registered and non-registered ones. And they are ways of setting parameters, effectively. So a registered parameter means that it's in the MIDI standard. It's got a standard address. It's something defined. A non-registered parameter means it is not in the MIDI standard. It differs by implementation user. So if you get an owner's manual for a synthesizer, it'll tell you the non-registered parameter. And you have to program your controlling device to send things appropriately. Okay? So the way they program these is actually use a controller command with special addresses. So if you set the controllers, if you use controllers 98 and 99, when you report the value for that controller, it's actually the address of the registered and non-registered parameter. So it's kind of like indirection. It's almost like a pointer. That 98, 99 are used as pointers for parameters. And similarly, 100 and 101 are used for the registered one. And then you have another value, which is called controller 6, which is where you actually send the data. So you use these, and you have the MSB and LSB, again separated by 20 hex, which is 32. And then there are also increment or decrement ones. So if you only want to alter it by a little bit, instead of programming the MSB and LSB again, you can just poke to the increment or decrement. So for an example, we got programming the pitch bend. So pitch bend is, like I said, pitch bend is so important it's got its own command. So it's also so important that it is registered parameter 00. So it's the first registered parameter. So what do? The first thing you do is you send the command, which is controller, and then you give it the, that should be registered parameter, not non-registered. Registered parameter, which is 100. So you say, okay, value 100, 0. Okay, value 101, 0. So that says, okay, I'm on the 0-0 pair. So I know that this guy wants to program the pitch bend range. Okay, so what you're looking at, really it's these 2 bytes that tell you what you're programming. Then you go here and say, okay, we know the address we're programming now. What's the value? Okay, well, we're programming controller 6, that's the value MSB, and we set that to value of 2, that's semitones. Okay, so the most significant bit on the pitch bend controller gives you the semitones. Now that you go, okay, so you program the least significant bit. The least significant bit tells you, tells you 1/100th of the semitone. So in a sense, it's actually, it's a bit of a misnomer to call the most significant byte and least significant byte, because they're not combined as a 14-bit value. Yeah, they're used independently. But the most significant is specified in number of semitones, and the lesser significant one is specified in hundredths of the semitone. So, okay. Next thing is, if we look at this, we say, well, this is crazy. We're sending the same command 4 times, and at 31 kilobits per second, that's gonna, that's 4 things we don't need to do. So what they did was they invented something called running status. And remember, status is the same as command. And so what that says is that instead of if you're sending the same command again and again, just keep sending the data. So if you know it's supposed to be 3 bytes long, well, if you don't send the command, it's 2 bytes long. And so it keeps going until you get a new command. How do you know when you get a command? Oh, well, the first bit is 1. So it's an easy format to pick out. And this also is very useful. Remember when we said velocity equals 0, the same as node off? Well, you can do running status with a series of nodes. So now you just do a running status with node on. You're always sending node on commands, and when nodes turn off, you just send the node on with velocity 0. So that's where node on velocity 0 becomes really useful when you do running status. So if you take that previous stream of programming with running status, now you see you've got the command, and then you've got MSB address, MSB, LSB address, LSB, MSB value, value, and LSB value. So you just save 3 bytes, which is significant at, again, 31 kilobits per second. Okay, channel modes. MIDI's got a way of specifying how a device reacts. You basically got omni, which means you can set the device to respond to node on any channel. So if you got 16 channels, you would normally program your up to 16 sound banks to respond to each channel. If you want to test that they're working, you can put them in omni mode, they'll respond to information on any channel. And so that's very useful. And that's really useful in a hard disk recording setup. Because you just plug in your controller, you set the hard disk recorder to omni, it records everything. And it doesn't care because each track is separate. So you don't need to specify the channels that's different within the MIDI and record on one track, if you can just record different MIDI on different tracks and keep them isolated that way. Polyphonic says you can create more than 1 pitch at a time. So that's the normal mode you would expect, and that listens to a channel. Monophonic, again, listens to a channel, but it only does 1 pitch at a time. And I'm not sure of the exact advantage of that, other than I guess you can just do it on command and automatically turns off the last.
It's kind of cool. I don't know. If you hold one down and hit the other thing.
Oh, okay.
It's sort of like more like a tapping.
Yeah, that would be, okay, that'd be pretty neat. Okay. Yeah.
I mean, it doesn't have much of an advantage, but it's slightly different.
Yeah, for little things, I guess it would make a difference. Like yeah, it's a great example where you want to hold down one and just alternate back and forth. I'll go play with it. That's pretty cool. Okay, patch change. This is saying, okay, often patches are different sounds. So you said patch change 0 would be grand piano, and patch change 10 maybe like a jazz organ. So there's a command to switch that. So sounds on the fly. So instead of having to program each device to create whatever sound it creates, you can change that on the fly. And then they went back and they re-standardized that. They made something called general MIDI, which allows, which is a standard set of these patch changes. So it used to be you had to configure each one separately. Now there's a general MIDI, and then there are, above that there are additional patches that you can specify. But the general MIDI is standard, so like grand piano.